Okay, so in this video we're going to be talking about the runtime analysis of different data structures and maybe some other stuff for C++ and pretty much just in general in any kind of computer programming. So usually what we're talking about is, when we're talking about runtime, is we care about worst case running time. And that's usually because a lot of times the best cases are too ideal for us to really consider. So we're just going to think about a couple of different data structures and try to think about what running time really means. So typically when we think about running time, the two things that come to mind are going to be search and insert. So search and insert, and I guess I'll make a little column right here for the structure. Okay, so let's just think first of all, what do we know? What's a simple thing? What about arrays, right? What about arrays? So we know what an array is, right? We know an array is just a sequential block of memory. And so the thing about arrays is, like, say you have, this is the first one, maybe memory address 1000, then 1004, 1008, and so on and so forth, right? So we can access any of these memory addresses at any time. So say this is, this is array A, and we want to get, say this is 2, 0, 1, 2, 3, and say the number 5 is right here. If we want to search for the number 3, we just go A of 2, and we get 3. So to get 3, all we have to do is just put that. And that doesn't take very long. We don't have to look through the whole array to find it. We just go immediately to where it is. So, so we would just write that this worst case running time is O of 1, right? So we just say this is O of 1. Now similarly, say I wanted to insert, say I wanted to enter the number 5 in index 3, right? I would just say A of 3 is equal to 5. These aren't exactly the same thing, but you can sort of understand the concept. That if I wanted to put 5 into 3, I just assign 5 to 3, and then we get 5 right there. So the insert, the worst case inserting time, is also O of 1. So arrays are really fast if you think about it, but they're not as interesting as some of the other data structures which we have to deal with. So let's just think about some other stuff. Linked list, right? So a linked list is a bunch of list nodes that are connected to each other. So a linked list is something like this. And so on. And there's also the root node, right? So if we want to search through a link, then let me just put some data: 3, 8, 2, 1. So this is the root. So if I want to search through this linked list, say I want to search for the number 1, right? I'm gonna have to go first. I have to start at the root, and then I have to go here, then I have to go to here, then I have to go to here, and then I have to go to here, and until I find the 1, right? Now, of course, 1 could be at the end of this list, right? So if I had a list and the length is equal to n, then that means that the worst case could be that the thing I'm looking for is at the end. So the search for lists, the worst case search, is going to be O of n. Okay? And then the thing about linked lists also that we've been dealing with is we just insert stuff at the front, right? So we just, because it's not really like ordered or anything, so if we want to insert something, I'll just create a new node, and I'll just point it right there, point it to the one before it. Say this has like, you know, a 4 in it or something, and then I'm just going to change this just to point to there instead. And so the insert, it only takes a constant amount of time, just a few instructions, and it goes right into the front. So we say that the worst case running time for insert is O of 1. Okay. So let's think, what are some other data structures that we know about? Well, there's also hash tables, right? So hash table. So a hash table, so there's several different ways to make a hash table. Let's try to think of one that we've done before. Well, when we did our project, right, we had like, it was kind of like an array, right? It was an array. This is like a vertical array, something like this, of lists, right? So like that, sort of, maybe over here. Okay. And something like this, right? So we're gonna say everything's n, right? So the hash table, this is a size n hash table, and that means that because we're going to be trying to talk about an ideal hash table, which means there's a universal hashing function which basically says that. So let's just try to maybe talk about that for 1 second, real quick. So if the table is size n, so if we want a hash table size n, right? So the table size n, and we want to insert m elements into the table. Okay, the size of the table is n, and we want to put m elements, right? We want to put m elements. Then, because we're using this function that's completely random and it doesn't have to do with the input distribution, that means that the probability of any input going to any of these locations is exactly the same. So because the probability of each of anything landing in any one of these indices of the array is going to be 1 out of n. The probability of something landing in any of them is 1 of n, no matter what. So because it's a 1 in n chance of anything landing in there, any input landing in one of these spaces, and we're going to be wanting to put m elements, then the average length of each list is going to be m divided by n. Okay? So typically, when we're putting stuff into the to a hash table, we sort of know the size of the table before we start doing it. So we would probably want to, if we know we want to put in n elements, we would probably want to make the table of size n. So if we, instead of, we're putting m elements, we're putting n elements into the table size n, then the length of each list should be n over n, or 1, right? So the goal of this is to try to make each list length 1, so we're pretty much not having that much trouble with searching. So anyway, though, we're talking about the worst case running time, right? So the worst case is, say that out of some miracle of some crazy thing that happened, every single thing that was put into the table mapped to the exact same location. And we're not considering that you could repeat the same number. We're saying that a bunch of different numbers went to the exact same location. Then it's possible that you would have just one linked list, right? So you wouldn't have this. You just would have everything would go to this one right here, and you have one linked list of length n. So because this hash table now is like a linked list, then the worst case search is O of n. And since it's an array of lists, since an array you can just you can insert into any element of array O of one time, and if each array is a list, each index in the array is a list, the insert is going to be O of 1, since the list you can insert at the front. So insert is going to be O of 1. Now what I said before is how, because of the universal hashing function, if we make it universal hashing, then this is going to be the probability of the length of each list. So this is like the probability of the length of each list. And so that's going to be 1. And so if I want to make like let me zoom out a little bit. So I'll just make a note. So I'll just write there. Let me erase this too. And let me just really erase this too, because this is not that important anymore. I'll make a notes thing. Note that search is probably O of 1, because of what we talked about. Okay, so that's for hash, and let's talk about for a tree, because that's probably like the confusinger one. Okay, so let's talk about for a tree. Alright, so how do we search through a tree? So let's just look about how a tree is organized. So let me just make like a funny little tree. Okay. And the property of this tree, it's a binary search tree. So we're going to say that anything to the left is smaller and anything to the right is larger. So let's say this is 15, 14, this is 8, this is 11, this is 20, and this is 17, and this is 21. Okay, so if I want to search for, say, I want to see if the number 17 is in there, right? So I would have to, I started here at 15, and I see is 17 bigger than 15 or smaller? I know it's bigger, so then I go here, right? And then I see this is 20, right? So 20 is 17 bigger or smaller? So then I see 17 is smaller, right? So then it took me two maneuvers to find 17. Now, okay, so right now we're trying to talk about worst case running time, right? So worst case running time. So a tree, there's a couple of properties with a tree. Now it doesn't have to be balanced or anything like that. So a tree could actually look something like this. So we're just going to be talking about the worst case right now. Here's a tree, right? Okay, so this is the tree, and it's some length long, but it doesn't matter. So say this is 15, this is 16, this is 17, this is 18, and this is entirely possible for a binary tree. So if we wanted to search for something, then we would have to actually go. Say we're looking for 18, right? We go 15, it's not there. We go to the 16, then it's not there. We go to the 17, it's bigger than that. So we finally get to the 18. So actually, search is actually O of n. right? So that's the worst case search is O of n. So see the tree right here, it's height 4, and we had to go, let's see, 1, 2, 3. So we had to go n minus 1, which is pretty much the same thing as n. So search is O of n. This is worst case again. And insert would be the same thing, right? Because we'd have to search to see if 18 is there, and then if it's not there, we'd have to put it in. So that would also be the same thing. Insert would be O of n. So it seems like trees are like even worse than normal things. But the thing is actually that trees are not usually going to be like this. And if you're just inserting numbers randomly into a tree, typically like it's not going to happen this way. So so typically trees are going to have some sort of an order to them. And usually, like if let's just look at like a perfect tree. Let's just look at a perfect tree. So a perfect tree would be like this. So this tree right here, so this is size 7, so there's, you know, n equals 7, and then the height is equal to 2. So if we look at this tree for a second, if we can see the reason the height's 2 is because there's 1, 2, and then there's 7 nodes. 1, 2, 3, 4, 5, 6, 7. So to actually discuss like the height of this tree from the number of nodes. Now this is actually a complete binary tree. We could say that this function is log base 2 of n, and the floor function of that is going to equal the height. Because log base 2 of n, right? So we know that log base 2 of, if n was 8, that's equal to 3, right? So then log 2 of 7 is equal to like 2 point, you know, something like that, right? And if we take the floor of 2.8, that's going to equal to 2. So if we're searching or inserting into this tree, we're never going to have to go like through the whole 7 things. We're going to have to just look through just for a few of them. You know, we might have to like go. I guess I should just put in some numbers there so it makes more sense. Let me zoom in a little bit too, or no, I'll zoom out, and I'll just make the tree bigger. Okay. Alright, so this is going to be hard. 15, 8, 23, 20, 25, 12, and then 5. So if I want to search for anything, it would just take, so if I want to find, you know, say I want to find 13, right? So I want to see is there 13 there, right? So at first I go to 15, right? And then I see is 13 bigger or less than 15. So 13 is less, so then I go to the left one, I go to 8. I see is 13 less than 15 or is 13 less or greater than 8. So I see 13 is greater than 8. I go to 12, and I see 13 greater than 12, and I say yes, 13 is greater than 12, but it's not there, so I'm done. So I only spent pretty much like log of n, so the size tree is 7, but I only spent about, let's say I went 1, 2, like pretty much 2 maneuvers to find that it wasn't there. So pretty much like trees aren't going to always be like this balanced, but overall they're going to have some sort of order to them that is going to make it so that searching through them is typically going to be log of n, so log of the size of the tree, and the log is log base 2. When we talk about trees, is log base 2. So we're going to say that it's the same sort of thing. So search is like O of log base 2, or like they sometimes put this in the book if you see it, LG, That just means log base 2 of n. So that's search. It's mostly like that, right? So then insert is it's sort of the same idea, because you're just gonna have to go and find. You're gonna have to search to the place that it is, and if it's not there, you're gonna replace it. You're gonna put it there. So you can see how search and insert are the same thing. It's like you search for it, it's not there, then you insert it. So is insert. So I think that'll be pretty much all I'll do for this. So I hope you understand the idea of worst case running time, and also what the running time is more like in most cases.